Greetings to everybody online. I'm very humbled by the response that's been reported to this talk that I am delighted to provide. I would say at the outset that I term myself an editor of the Nuclear Propulsion Roadmap for Australia because it's my fervent hope to enlist many more people to write with great authority on their own particular areas of interest and experience to build up a collective, if you like, of people committed to this future. Nevertheless, the Nuclear Propulsion Roadmap for Australia is a registered business name of my own company. I would like to make a disclaimer. I'm not a naval architect, I'm not a nuclear engineer, and I'm not a submariner. And so what I'm talking about is based purely on my own desk research of open source material. I'm well aware there are many people in the audience tonight who've got profoundly more insight and knowledge than I do in the various topics, and I will very much welcome their comment or criticism or contribution to raise the depth and the precision of what I have to say from my own humble level. So, what are we talking about? Well, this is a brilliant cutaway drawing of the lead ship of the Suffren class for the Marine Nationale French Navy, and it's termed the Barracuda design, which of course is also serving as the reference for our own attack class. Now, by reference, it does not mean conversion, as some people believe. It means that in terms of macro numbers, in terms of size, weight, and dynamic factors such as drag and so on, that the numbers that are found for the Suffren will have some similarities for the attack. So it helps in the process of the design, which is ongoing at the moment. The other thing I'd like to draw your attention to is the after part of the submarine, the area which I'm sure you can work out for yourself is the actual reactor compartment, some auxiliary machinery, and then some of the main steam plant, which is the propulsion train. And why I want to draw your attention to it is that the mass, particularly of the reactor containment vessel and associated items, is quite considerable. So from a naval architecture point of view, achieving the essential static balances that a submarine must attain, that is neutral buoyancy, balance fore and aft, and athwartships, means taking into account that very large mass. This is in a counterpoint to what we're doing with the attack class, where the main mass will be the battery, which, as in the Suffren, is distributed along the length of the sort of central 2/3 of the boat, and therefore, from a naval architecture perspective, presents quite a different challenge in terms of static balance in the design. And that probably is the limit of my naval architecture insight, and may even be misleading, and I'll welcome any comments to that effect. What am I going to cover? Well, the outline, the roadmap that I've been working on for a couple of years now, I've decided should have 10 sections, and these are the sections, and I've laid out this talk along the same lines. Why do we want nuclear propulsion? What's the history of it? what are the challenges for Australia in particular? What is the nuclear fuel cycle, which is a very important factor that back in the early days, in the height of the Cold War and the confrontation with the Soviet Union, was not clearly thought through till its final conclusion, as I'll enlarge later. But in the current day and age, and particularly in Australia, we must think through the entire nuclear fuel cycle and have a satisfactory way of dealing with it. There's quite a lot of infrastructure over and above what's needed for any submarine program. I talk a little bit about construction from what I know of it. I've visited ASC in South Australia. I've seen what happens when the pressure hull is firstly penetrated with a large workspace or work access, and then actually separated into two sections. But that's it. The welding back together or the replacement of the patch that's removed is a very challenging thing, but we've got 30 years of experience at ASC, and now we've got the additional experience of Naval Group. So I'm quite confident we know how to do that. Furthermore, I think those people who are into metallurgical science would say that we've been doing some of this sort of work for some time in other offshore and subsea structures and chemical plants and so on. It's not completely different by any means. We must ensure that the regulation is properly handled, and luckily we're a long way down that track, except we don't have any nuclear power plants and we don't have any nuclear submarines or other vessels. But assuming, as I and some others do, that we should and can get started on nuclear propulsion before we've got lots of nuclear power plants and a nuclear industry more generally, then how does it work in reverse? What would be the implications for a power industry by getting started in this way? And finally, just some throwaway ideas on timelines. And as I'm sure everybody on the call will be well aware, the timeline for our current two submarine programs are very, very much a long way from being ideal. The fact that we're unavoidably committing to an extensive extension of life for the Collins class because of the failure to address a replacement, let alone an expansion or a doubling in size of the submarine force. We cannot countenance that sort of neglect or procrastination in the future. Anyway, moving on. Here's a little bit of nuclear fission that I'm sure the experts in the audience will worry about. But according to the reference that I have, each fission takes a neutron, provided it is moderated to a lower speed, lower velocity, and this can then create a single fission, produces some fission products, which are various other isotopes of smaller nuclear number elements, but most importantly produces some more neutrons plus gives off thermal energy, and that's the secret of what's going on with nuclear energy. According to my reference, which is listed here, each fission generates about 200 mega electron volts, of which a lot of it is available and is not absorbed or dissipated or leaked. And by what my reference says, this means that to produce 1 megawatt of thermal energy per day requires the expenditure of 1.3 grams of fuel. Einstein really gave us a lot of insight of the transposition of mass into energy. But for a submarine that we're talking about a 10-year operation, if we were looking at it staying at full power for that entire period, or let's say 100 megawatt thermal, that's equivalent to the consumption of 474 kilograms of fuel, or the uranium 235 content in that fuel. Now, I'm not going to dwell on that or try to expand it. That's about the limit of my professed knowledge in this sort of area. But what it does, I think, prove is that the need for refueling is a non-trivial aspect. And just blithely saying, oh, well, the US Navy and the Royal Navy have got highly enriched fuel and therefore they don't need to refuel, does not really solve the problem. The other aspects of how they operate may well be either undesirable or unacceptable for Australian practice, and therefore I think it's more reasonable that we take the more conventional, shall I say, or the more predictable operation that, say, France uses, where they expect to refuel every main cycle, that is 10 or 12 years. Anyway, moving right along, why do we need nuclear propulsion for submarines? Virtually unlimited energy, endurance only limited by other factors, much greater sustained speed, and most importantly, avoidance of the need to snort. Even with air-independent propulsion, that has the consequential effects that you're carrying additional supplies, fuel and or oxidant, and thereby limiting your endurance. So there's a trade-off, and so that still applies even with AIP. And most importantly for Australia, unlike Canada, we've got very large transit times if we are going to place our submarines in the likely optimum locations to provide the deterrent factor that we need, since we don't have any other major long-range deterrent at the moment and may not have any other in the foreseeable future. Peter Briggs and others have written extensively on this. The first such writing was by the late Rear Admiral Andrew Robertson, and he and colleagues wrote a couple of really interesting pieces, and there have been a number of others since then, which I won't dwell on, and I leave it to you to do a Google search. You'll find several of them, and this is what we're talking about. Now, the history of nuclear propulsion, well, it all started with Admiral Rickover, and the USS Nautilus was the first such vessel. It was underway on nuclear power in 1955, and there's an enormous wealth of writing about how that all came about. And what I think is important is, after Rickover had got the Nautilus program well and truly underway, he was then sent off to Shippingport to start up a nuclear power plant in that order. And so I think that's something to remember when we talk about Australia approaching nuclear propulsion before perhaps nuclear power stations. Now, I won't dwell on this, but most submarines use pressurized light water reactors, and there are a couple of good reasons for why that is so, and why also PWRs are the most common current reactor technology for nuclear power stations. Firstly, the temperature density profile has an inherent negative feedback effect. If the temperature starts to rise, the density decreases, and therefore the effects of the water as a moderator decreases, so which has therefore a reduction in fission activity. And the other big advantage is that while it's a very or quite effective moderator for the neutron flux, it's also the cooling medium. So you get both characteristics in the same material. Quite as a result of the insistence by Admiral Rickover on the most absolutely minute attention to safety and material quality and standards and practices, there have been nil Western submarine reactor accidents reported. There have been some such reactor accidents in Russia and possibly elsewhere as well. However, as I alluded to earlier, the full reactor or the full nuclear fuel cycle was not fully resolved at the start of all of this work because of the confrontation with the Soviet Union. And so consequently, the USA has sort of got there. They removed the reactor section and any other radioactive material, and they bury it literally in a great big hole in the ground. That's their disposal. The UK still hasn't got that far. They've got a huge effort going on for the national decontamination and so on. I can't remember the full name of it now, but they're actively working on it. But as in 2 years ago, their National Audit Office reported that of the 20 decommissioned nuclear submarines, 7 of them still hadn't been defueled, and the others had not been properly decontaminated yet. Russia's even far worse. They just take them up to the Arctic Circle and park them somewhere, and sooner or later they sink. And you know, it's very unsatisfactory, and there's no way that Australia could ever take on a program with that sort of attitude, but particularly because it's Australia, but also because we're no longer in that very fraught nuclear confrontation. And nuclear submarines, of course, are also in service in China and France, and India has got one they've built themselves, and they're going to build a couple more, but they started out working with Russia. So moving right along, Rickover was absolute character, and here's one of his many quotable quotes. But this is the sort of serious way that Rickover went about things. This is the test rig for the reactor that went into the Nautilus. And what he was insisting was that, firstly, the reactor would fit completely within the pressure hull dimensions, and there were no extra bits that were needed and just wouldn't fit. But more importantly, that it would put up with the normal motion and the power variations that a submarine must have or must experience. And so this was the actual rig that was used to, with the reactor inside it, to prove that it worked successfully, even though this floating sort of dummy pressure hull was being rocked and rolled by those various arms that you can see, and cycled in terms of power excursions. So, challenges for Australia. Well, we've made a start on thinking about it. Professor Tom Frame chaired a very successful full-day event, which was run by the Submarine Institute of Australia, where I need to declare an interest. I happen to still be the treasurer there, but I did not take any active role in producing this one-day event. But anyway, from that, this book has been published and is now readily available. And it addresses some of the things that I've mentioned already. In particular, the legislative bans that specifically prohibit 4 things: enrichment, fuel fabrication, power plant operation, and or the reprocessing of spent fuel. And it's interesting why it's so specific. Obviously, the authors of that legislation were trying to think of any loopholes that they wanted to make sure were not there. Funnily enough, though, and including all of the more recent reviews of nuclear power in Australia, there was no specific mention of nuclear propulsion. And that's pretty important because it means there's no actual legislative ban on starting to talk about nuclear propulsion. What we can't do, though, is all of the sustainment and other infrastructure that would be needed until those bans are modified. But the throwaway line that the nuclear industry is a prerequisite is far too vague and open to challenge, and that's what this book neatly encapsulates in the various chapters that are written by experts in the field. We will need, of course, to draw on overseas expertise. I'm quite sure we won't be going to Russia, but I do think UK, USA, and perhaps more recently also we should give special mention of France. Now, here is a generic submarine with the nuclear plant very visible in the left-hand side of it, or the after part of it. And I think what I want to draw out from this is the relative size, dimensions, the longitudinal relationships and so on. The reactor towards the middle, the steam plant and drive and gearing and so on aft, some auxiliary machinery, the after escape hatches back there, because there's a team of ship's company operating that after propulsion section, and they do it from the maneuvering room in this particular design, which is this area just after the reactor compartment. And that means they've got ready access to all of the steam plant and the auxiliary machinery and so on, which of course is dealing lots of things, including air purification and all the other services that are needed. This is another view of a different submarine, and I only included it because it's got more detail of the reactor compartment. What I hope it shows is why I said earlier about the very large mass of the reactor compartment and the reactor itself. That's all I wanted to bring out on that slide. Now, what are we talking about the nuclear fuel cycle? Well, you know, Australia's got the largest resources of uranium ores. We sell it overseas, including to India, even though we had some difficulty with their unwillingness to sign up to some of the international treaties. Milling means taking it back to a more useful level of content. Processing to make it more portable. Enriching it to raise the percentage of the fissile material, that is the U235, to a higher level than the natural level, which is about 0.7%. Manufacture of fuel assemblies. Now, this is actually a very detailed and challenging activity, but it's very well understood worldwide because a lot of it's been done, or it's been going on for some time by a lot of people, I should say. The fuel assemblies have got to be such that the actual fission itself does not lead to any localized areas that overheat and thereby damage or even cause the material to melt or to deform. And yet it's also got to be accessible for the water moderator and to be controllable, let's put it that way. Fueling the reactor means a number of assemblies that have just been created, arranged into a particular shape, which is also a very detailed process that needs to be undergone. The reactor then operated over whatever cycle there is between refueling. And that means that initially you'll have an excess of fissile material, so that as the reaction proceeds over months or years, it remains sufficient to continue the reaction for as long as you want it to. But in order to ensure that it doesn't overreact at the beginning, then typically there will be some form of doping or poisoning, as it's called, of the moderator to absorb more of the neutrons in the earlier stages and less as time goes on. That's operating the reactor is not just turning knobs or levers or lifting rods or whatever. There's quite a lot of chemistry to it as well, which I won't attempt to detail because it's above my head. The time then comes to refuel, or even at the end of life to defuel, and that means you've got a whole lot of spent fuel that you have to deal with, and it's active and very hot and needs to be cooled for a period of years while the ongoing radioactivity decays to a level where you can then think about reprocessing it, removing the fuel that is still usable, removing other desirable or undesirable byproducts, and then what's left, the hazardous material, disposing of that perhaps in some encapsulated form. I'm not going to dwell any more on it than that, but it's those last few stages that were not fully thought through in the early programs because of the reasons I've given. And I won't dwell on this slide, but this shows the cyclic nature of the fuel cycle. And in the interest of time, I'll leave that for others to study in more detail when this slideshow is put on YouTube by the Royal Institute of Naval Architects, for which I'm very grateful. Infrastructure, well, fuel processing, fueling, etc. Storage of spent fuel, I've mentioned all of that. And so I just have got these sort of book covers of relevant references that I've included in a bibliography that may be worth following up. Now, one of the very important factors that I've noted is that with a nuclear submarine, there's one significant difference. You can't just shut it down and that's the end of it, go on to shore power or whatever. The reactor must be kept cooled indefinitely. Once it's gone to critical and starts, the fission process starts, it continues and it must be cooled. And that means that no matter where you are, including something like this floating dock, you must have a continuous source of cooling for the reactor and a backup, at least, maybe even more than one backup, to ensure that there's never any likelihood of that cooling being interrupted. This was a study done by the RAND Corp, and I contacted them recently to see if they'd be interested in doing one on nuclear propulsion. They said they'd be delighted, but they only ever take contracts from the government, and the government isn't quite ready yet, but it'll come. Now, why would what would be the issues that we need to think about? Well, a lot of this would come from overseas, and it may even be that for the earlier submarines that we accept the fact that the after sections of the submarine, mainly the reactor and all the steam plant and propulsion drive, will be imported and welded to the front end, which we might be prepared to do ourselves. Now, that would be safely undertaken if the reactor is built, fueled, but has not been activated. That is, it has not been taken to criticality, and so the fission process has not started. And the bottom bullet here indicates that there has been a study in the UK that it's possible to do this and then move the inactive submarine to a different site before activating the reactor. So therefore, it's feasible to do it, to build a reactor overseas, bring it to Osborne, and mate it up with the forward part of the submarine, which we would build locally. I won't dwell on this. This is just a nice sort of glossy one of what sort of the environment is for building submarines. This is a more exploded view, and again, I won't dwell on it in the interest of time. Most importantly, though, the various modules or sections of the pressure hull, the main parts of them are cylindrical, and the way of building is to build them in modules of, say, 10, 15, 20 meters length, and, well, not 20, 10 or 15, and then to slide in this raft of all the machinery that goes with it before mating up that module with the one forward or aft of it. And that has another important benefit, that you can also take the time to insulate from the vibration and other acoustic transmission of this raft from the pressure hull, which contributes to acoustic quieting of the submarine. Now, this is the overall propulsion flow diagram. And the point I wanted to make here is the reactor compartment on the left of this is a discrete piece of the pressure hull section, and then all of the propulsion after that. And it's my contention that they could be built separately and then mated at the assembly site, and then the pair of them mated to the forward part of the submarine. And this is an actual view of a reactor unit of a French submarine that is typical of how this might be done. As you can see, it says DCN. Well, now they're called Naval Group, but this is what it would look like. And recently, Professor Stephen Wilson, I think I mentioned this, no, I didn't, but anyway, he recently gave a presentation on a study done at the University of Queensland about the adoption of small modular reactors. And I asked the question, would the adoption of nuclear propulsion assist? And he basically thought about it and said, yeah, actually it might. And furthermore, it would perhaps lead to a synergy between the manufacture of large pressure vessels, such as submarine pressure hull, or chemical plants for that matter, with small modular reactors. And this is what an SMR reactor containment vessel and reactor vessel itself might look like. These are taken from the NuScale plant, which is under construction now in the USA. And it shows two things. Firstly, the internal arrangement of the reactor core at the bottom and the various control and cooling and steam generation parts of the reactor, and on the left the way in which it can be transportable, and that I think means that it's not unlike what we're talking about for submarines. Now, regulation, well, we've got ANSTO, that's a very highly regarded internationally, and operates in sites both in New South Wales and in Victoria. We also have RPANSA, and RPANSA is a very impressive organisation that a lot of people have not heard of, but Australia allows the visits of nuclear-powered warships to selected ports, and the rules of how that should be regulated are issued by RPANSA, and they're available online for anybody to read. And they have in there the reference accident. In other words, if you're planning for what might go wrong if there were a nuclear accident, what sort of factors should you take into account? And it's well worth reading. However, because of the reasons that were foremost in the mind of Admiral Rickover, we need a bit more than that. We've got to think about the shock and vibration and the operating cycle in terms of demand for a submarine compared with a power plant. And secondly, a very much longer period between refueling compared with a power plant. A normal nuclear power station refuels every 18 months, whereas we're talking about 10 to 12 years minimum, let alone the UK and the US going for 30 years. Workforce, well, we could spend a lot of time talking about this, but it will be a very, very big program to build up the workforce, both uniform and in the industry. But I think we could probably attract people from overseas, from one of the three countries that I've mentioned, and fit in readily in how we go about this. The training, though, is a non-trivial task, and this is just an example of what goes on in India to train their nuclear submariners. This is an actual light water reactor that they run on shore to train their nuclear submariners. Oops, too fast. So the implications for the civil power, well, SMRs are on the way. The arguments now have moved from they're prohibited to they're too expensive, says CSIRO, which has been disputed. But with SMRs, there are some significant advantages which make them more likely to be adopted in the nearer term. And what I think will be very apparent, as has occurred in other countries, that the Navy bringing forward a workforce for submarines at the same time or concurrently with putting in small modular reactors will be a very synergistic process. So timelines, well, I won't dwell on all the detail of this, but we've got 2 submarine programs underway at the moment. As I said earlier, if we hadn't been so slack in getting started on the attack program, we wouldn't need the life of type extension for the Collins, but that's going to happen. And here are some timelines. And about the time that the last of the Collins life extension occurs would be when I would see us starting work on building the first of our nuclear submarines, albeit with the after section, the propulsion section, being brought in from overseas and then assembled or welded together here. What I'm assuming is that the attack class, which needs to get cracking just as soon as we can, and you know, it's on track. I'm not criticizing what we're doing now. There are all sorts of arguments about Australian industry participation and so on, which again, we could be distracted with, but you know, they'll go on. But anyway, more importantly, I think that's got to get cracking and deliver at least 6 attack class. And if we get our act together, we can deliver the first of the nukes immediately following that. So what I've put here is that the first of the Australian nuclear submarines would deliver shortly after the 6th of the attack class. I'm assuming that we'll need another few more years of going round and round and trying to convince everybody this is a good thing to do, that it's not going to be dangerous, and that it's essential for our geopolitical and other strategic reasons, and that we'll decide to get cracking on this in 2028. And I'm hopeful that that date will be achieved. And so in conclusion, SSNs, that is nuclear submarines, provide a much greater capability. SMRs are licensed and under construction, and they are applicable for Australia, as UQ has been studying. SMR power levels are comparable to nuclear submarine reactors. I didn't make that point, but we're talking, an SMR is defined as up to 300 megawatt thermal. Typical submarine is about 100 megawatt. They're comparable. Workforce education are similar. There are some additional things for the naval people, but that can all be dealt with. Our Panzer exists and is highly respected. We might need a bit, well, we will need a bit more than that to deal with naval reactors. We need some specialized infrastructure, and we definitely need, as the last bullet says, to plan for the entire nuclear fuel cycle right through to disposal of the remaining waste and the decontaminated material from the actual submarine. So without further ado, here's the bibliography that will be available for people to study later. And I welcome discussion.